Why does time slow down when you move faster? At the beginning of the 20th century, physicists faced a problem that didn't behave like any other problem in science. It wasn't about weapons, it wasn't about planets. It was about something invisible but universal: time. For centuries, time had been assumed to be simple, a constant flow, the same everywhere. Whether in London, Paris, or Cairo, 1 second was always 1 second. But that idea was about to collapse. A German-born physicist named Albert Einstein began asking a disturbing question. What if time is not absolute? What if it changes depending on where you are or how fast you move? If time is not the same everywhere, who decides what real time is? At first, this idea sounded impossible, because in everyday life, nothing seems to change. A clock ticks the same on a train, in a house, or in a city square. But Einstein suspected something deeper was happening, hidden from human senses. In 1905, he introduced the concept of special relativity, a framework that changed one simple assumption. The speed of light is constant for everyone, no matter how fast you move. That single idea breaks intuition, because if light is constant, something else must adjust, and that something is time itself. Imagine two observers, one standing still, one moving very fast. Both measure the same event, but they do not agree on how much time passed. 1 second for one person might not be 1 second for the other. If two people experience different time, who is actually correct? This is not philosophy, it is physics, and it has been tested. Even modern technology depends on it. Satellites in orbit carry extremely precise atomic clocks, but they are moving fast around Earth, and they are also farther from Earth's gravity. Both effects change time slightly. If we ignored these differences, systems like GPS would drift by kilometers every single day. Your phone navigation would become useless very quickly. So engineers must constantly correct time using relativity. If we need physics to correct time, is time really as stable as we think? Einstein's idea also leads to a more extreme conclusion. If you move close to the speed of light, time slows down significantly compared to someone standing still. To you, everything feels normal, but outside your frame, time is moving faster. This means a strange possibility appears in theory. Traveling fast enough could allow you to reach the future of someone else's timeline. Not science fiction, a direct consequence of physics. But there is a limit. Nothing with mass can reach the speed of light, because as the speed increases, energy requirements grow dramatically. Approaching light speed requires infinite energy. If the universe allows time to stretch, why does it also block us from controlling it freely? By the early 20th century, time was no longer a universal background. It had become flexible, dependent on motion, dependent on gravity, dependent on perspective. And this was only the beginning, because Einstein would later expand this idea even further into something even more extreme. Not just time changing, but space itself bending around it. And once space starts bending, the question is no longer how fast you move. The question becomes, what is holding the universe together at all? When time becomes a curve. By the time Einstein expanded his ideas, the problem was no longer just about clocks, it was about reality itself. Because if time can change, then space cannot stay fixed. And if space is not fixed, then the entire structure of the universe is flexible. This led to the theory of general relativity. In this framework, gravity is not a force pulling objects. It is the bending of space and time itself. If gravity is not a force, what is actually pulling you to the ground? Einstein described space-time like a fabric. Massive objects like Earth, the Sun, or black holes bend this fabric. Smaller objects simply follow the curves. What we feel as falling is actually movement along distorted space. Now time enters the picture again, because space and time are not separate anymore. They are part of one system, space-time. And if space bends, time bends with it. Near strong gravity, time slows down, not metaphorically, literally. A clock closer to a massive object ticks slower than a clock farther away. If time changes near gravity, does that mean reality is different depending on where you stand? This effect is not theoretical anymore. It has been measured. Even astronauts experience tiny differences in time compared to people on Earth, and near extreme objects, the effect becomes dramatic. Around a black hole, time can slow so much that minutes there could equal years elsewhere. From the outside, it would look like everything is frozen near the edge. If time can almost stop near extreme gravity, what does that say about the beginning of the universe? Einstein's equations also point backward. If space-time can expand, curve, and stretch, then it must have had a beginning. This leads to the idea of the Big Bang, not an explosion in space, but an expansion of space itself. And suddenly, time has a boundary, a point where asking before may not even make sense, because before time is not a normal direction in physics. If time itself had a beginning, what existed before it? Modern physics still struggles with this question, because every answer seems to lead to another layer of uncertainty. Quantum physics suggests randomness at small scales. Relativity describes smooth curvature at large scales. But they do not fully agree with each other yet, so we are left with a strange situation. We can calculate time dilation precisely. We can correct GPS satellites. We can measure gravitational time shifts, but we still do not fully understand what time is. And maybe that is the most important conclusion. Time is not just something we measure, it is something we are inside of, something we move through, and something that may not behave the same way everywhere in the universe. If time can bend, slow down, and stretch, are we living inside time, or is time living inside us? Can we actually travel through time? For centuries, time travel belonged to myths, legends, and novels, from the time machine to modern science fiction. People imagine stepping into a machine and moving through history like walking between rooms. But modern physics produced an uncomfortable surprise. Part of time travel is not fiction, it is real. What if humanity has already traveled through time? In fact, astronauts have. Not dramatically, not by centuries, but by tiny fractions of a second. Because of relativity, astronauts aboard spacecraft experience time slightly differently than people on Earth. When they return, they are technically a little younger than they would have been if they had remained on the ground. The difference is small, the principle is enormous. The Soviet cosmonaut Sergei Kriklev, who spent hundreds of days in orbit, is often cited as one of the most significant examples of this effect. By moving rapidly through space and spending time away from Earth's gravitational field, he effectively traveled a tiny amount into Earth's future. Not enough to notice, but enough to measure. If traveling into the future is possible, why can't we travel into the past? That's where physics becomes far less certain. According to current understanding, moving forward in time is relatively straightforward. Just move very fast, or spend time near intense gravity. The challenge is going backward, because the past creates paradoxes. Imagine preventing your own birth, or stopping an event that caused you to travel back in the first place. Physicists call these causal paradoxes, and they create serious problems for any theory of backward time travel. If the past cannot be changed, why do some equations allow strange shortcuts through spacetime? This leads us to one of the most fascinating ideas in theoretical physics: wormholes. A wormhole is a hypothetical tunnel connecting distant regions of spacetime. Imagine folding a piece of paper. Two distant points suddenly touch. A wormhole would do something similar for the universe. Some solutions to Einstein's equations suggest such structures might be possible, but there is a problem, a very large problem. No one has ever found one, and even if they exist, they may require forms of matter and energy we do not know how to create. Meanwhile, black holes continue to raise questions. Near them, time behaves so strangely that even experienced physicists struggle to describe the experience intuitively. The closer you approach the event horizon, the more dramatic the distortion becomes. To an outside observer, your clock appears too slow. To you, it seems normal. Both perspectives are correct. Can two people witness different versions of time and both be right? Perhaps the strangest conclusion is this: time may not be as fundamental as we once believed. Some modern theories suggest time could emerge from deeper physical processes, just as temperature emerges from the motion of atoms. If that is true, then humanity's understanding of time today may resemble astronomy before the telescope: useful, but incomplete. The philosopher Saint Augustine once wrote, "What then is time? If no one asks me, I know. If I wish to explain it, I do not." More than 1500 years later, that sentence remains surprisingly relevant. Because after relativity, black holes, quantum mechanics, and space exploration, time is still one of the deepest mysteries we have ever encountered. And perhaps the biggest question is not whether we can travel through time, but whether we truly understand what time is in the first place. And as always, if you enjoyed today's journey, consider subscribing. There are many more stories waiting to be told.